Hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we are going to start lecture 16. So, in the previous lecture we have written the MATLAB code for a fixed point method. So, today we will start with the MATLAB code of the Newton-Raphson method. So, let us write this one. So, in the previous class we have shown that the rate of convergence was 0.2. So, I will just write the CLC and clear all. Now, based on this one, so this is my fixed point iteration. So, I will start writing a new code. So, let us define a function. So, the output of this function is I want my solution and the number of iterations, and then I want X list. So, I want only 3 output from there. So, that is equal to, I will write Newton method. In the argument the function f will be passed, the derivative of the function will be passed, the initial data and the tolerance. So, this is the requirement of the Newton-Raphson methods. Now, from the Newton-Raphson method I will write. So, from here I can write that the and from here we know that that is equal to x at x new, I can write is equal to x old minus minus f of this is at x old divided by the f dash, the derivative of this one at x old, because we are talking about only the simple root. So, that is the equation. So, it means that my whatever the a I am getting is, I will write it a old is equal to a. So, I will this value will be saved in the a old, the new variable I am defining. I will start my ITR is equal to 0, then I will define my X list. So, the value of this is equal to the initial a, whatever we have, and then I can define my f printf. So, it will gives you that. So, I will write at the initial, the new line, and I will write my the initial approximation or initial guess So, I will define my a here, that is equal to percent 7.6 f, and then so after that I can define my new line. So, and then I can give the value of a, semicolon. So, it will give you show you that the initial approximation. Now, I will write the while loop. So, value of the while loop is I am finding that the absolute value. So, whatever the f I am passing, so I will evaluate the value of f at a old. Okay. So, if value of this f a old, the absolute value I am taking, and if this is greater than the tolerance, so it will come out from this one. Now, I am defining the AND operator, so logical AND operator, and this will happen if ITR is less than 100. So, this while loop I will enter the while loop when this value and this value both are true. If either of them is non true, then this will come out from the while loop. So, I am finding that what is the value of the f at the root if it is either greater than tolerance and the iteration is less than 100. So, in that case I will enter there and then I will find my A new. So, A new will be A old minus, so what I want is the value of the function at A old divided by df at A old. So, this one I will define. So, A old minus f old divided by A f old. So, from here I will get my value of A new. Now, I will write A old is equal to A new. So, I will pass this value to the A old. I will write my iteration is equal to ITR incremented by 1, and then I will put my X list. So, this I can put my X list is equal to ITR plus 1. So, that is equal to A. So, whatever the A new or A old, because here it is value same, I will put the value here, and then I will write from here, I will write my value of f print f. So, f print f I am writing at ITR iteration is equal to d, the value of A is my, so this will I will remove. So, I will put A and then this I will put f at A. So, f at A is equal to again 7.6 f. So, that is a 7.6 f, and then I will put the new line, that is the new line, and then I will pass here the arguments, that is ITR. So, ITR is the first one, then the value of A. So, A means I will now putting my A old or A new, does not matter. So, A old, and this is the value of the A old, and now I want my f. So, I will define my f at A old. And now it will closing down, and then I will write ending of the loop. Then my solution is A new and iteration, or I can write from here number of iteration. So, I can point number ITR. So, that is equal to ITR. So, that is the Newton-Raphson method. I can save this one as Newton. So, this is the Newton-Raphson method now. Now, I can change in the main loop. So, now everything will be same except all these terms. Up to here I can, now everything will be same here. So, maybe I can so the same code I will use for Newton method. So, in the Newton methods we define the new function. So, let us write down the function. So, let us I take f is equal to at the rate, maybe I will take a simple function. So, let x raised to power square, okay, minus maybe I will take 9. So, this is the function I am defining. Then I define df. So, df that will be 2x. So, this is the value of the 2x. Now, I know that from this equation the x exact is equal to 3 or minus 3. So, in this case we have a roots x square is equal to 9. So, x is plus minus 3. So, I just looking for the positive root. So, I will just take x exact is equal to 3. Now, in this case, so other things I will just print from the above and I will write and I will comment this one. Now, my f is this one and this is the root I am finding. So, here I am having the 4 outputs. So, let us see that how many outputs are there in Newton. So, you can see that solution, number of iteration and x list. So, we have only 3 number of outputs. So, I have to change this one. So, I am getting this. So, I am not passing the value of the function at that. So, I am passing my root and iteration in the list and this is the value I am passing. So, fixed. Now, I have to change this one to Newton. So, in the Newton I am passing my f, my df, the value of A and the tolerance. So, from here I am getting my x list, x exact, this is the value and that is the convergence. So, I hope this should work. So, I will just save this one and run this. So, let us see what is happening here. Undefined function or variable A in the main. So, this is my main. So, my A is I am suppose 3 is the root. So, let us start with 2. So, I am starting with the A is equal to 2. Now, let us see. So, undefined the tolerance because I have not defined the tolerance there. So, let us define the tolerance also. So, I will define the same tolerance. Now, it is done and that is the solution. So, from here you can see that I started with the A is equal to 2 and then my roots approximation to the roots is first approximation it is giving A is equal to 3.25, that is the value of the function, and after the 4 iteration it gives you the value 3 exactly and that is the value of the function at this 0 0 0 and the rate of convergence it started with 2.35 then 1.98 and after that it is giving 2. And we also know that this rate of convergence for the Newton-Raphson method is of order 2. So, in this case it is coming exactly 2 because in this case I am also getting the exact root that is equal to 3 because in the previous case we are getting the exact root is equal to 2.331. So, that is also the approximation root of that, but in this case it is giving you the same value. So, maybe I can change this one and let us take minus 3 and I will start to maybe minus 1. So, let us see what will happen. So, in this case it is giving the 2 or that infinity is like it is coming like because somewhere we have to find the value of absolute value. So, it started with 1 then minus 5 then minus 3 minus 3 minus 3 and then it coming to 3 because the initial approximation if you see from the Newton-Raphson method we have the sufficient condition for the convergence. So, that sufficient condition we have to take care whenever we start with the initial condition. So, here I am starting just with the A raised to minus 1 and then later on we found that we are reaching toward the root and root is minus 3 and then the rate of convergence here also coming 2. So, that we have to take care. Maybe I can start with some another equation and then let us write it. So, in this case what is happening? I am getting my exact root that is 2. This will be 3 star x raised to power 2, and then I will start with suppose 1. So, let us see this one, and then I will find out the root here, or that is the equation. So, I will start it with 1, then it is giving the first iteration, and after the 6th iteration I am getting the root, that is 2, and the rate of convergence is 2. So, in this case we can see that Newton-Raphson methods, we started with the simple equation, and after doing this one we are able to find that the rate of convergence for the Newton-Raphson is 2. So, that is all about that how we can find the Newton-Raphson method. Now, we can write the new code also. So, let us start with the new code, and that code we are going to define is basically regular falsy. So, let us do the code of regular falsy. So, in this case of I will define the function, and then I will find the value of root and iteration, the number of iterations, and then x list, and then I will find regular, and then in this regular I will pass my function f the initial 2 guess, because here we have to give the 2 guesses, and then the tolerance. So, this is the function regular we have to define, and then so in this case also I can write that what is the value of this one. So, from here I can write if the value of f at a multiplied by the value of f at b. So, that is the value of f a and f b is suppose is greater than 0. Then I can show the display that no root lie in the interval AB. So, this is the value I can define from and then it will just return and then add, because in this case I know that intermediate value theorem will not be satisfied and there will be no root. So, I will start with this one now. So, instead of writing again and again the same thing, I maybe just copy. So, I will open bisection method, because it is same close to the bisection method. So, I will just, because in the bisection method we had the advantage that we can find the number of iteration we are going to do to get to achieve that accuracy of the root, but in this case we cannot do that. So, I will start with the iteration 0 and that is the value. So, I just copy paste from here and I can apply here. So, I start with the iteration equal to 0 and then at the iteration 0 initial value A and B I can define. So, this is the value it will be shown. Now, I will again write the same thing. So, I will copy this fixed point Newton. So, I will write this and then I will control V. So, when the absolute value of f at f old. So, in this case I have to define the value of maybe C. So, let us write my C is equal to, so I have to write what is my regular falsy method. So, B minus f at B minus multiply by B minus A, that is divided by f at b minus f at a. So, this is the value I am getting. So, this is so f b star b minus a divided by f b minus f a. Yeah. So, this is the value we are getting, the value of the C, and now I will put the value of C here. C. So, if the value of the f c is greater than tolerance and the iteration is less than 100, then I should enter here. So, once I enter here, I will get the value of C, because I am. So, this C will be again calculated, does not matter, because this C is needed, because it may happen that whatever the value I pass, on the first iteration itself I get the root. So, if I get the root and the value of the f c becomes less than tolerance, then we have to stop there, right. So, that is why we write this one, and then now I write if the value at C is equal to 0. So, that is the one condition, then my A will be C and B will be C, right, else if. So, else if means if f of B star f of C, so that is the value we have to find. If it is greater than 0, then what will happen? B becomes C, else A become C. So, in that case my A becomes C, and then it will be end this if loop, and after that my ITR becomes ITR plus 1. So, before here I have to start my x list is 1. So, that is equal to the value A, and x least 2 is B. So, I have saved my value of initial guess A and B in this one, and now I put x list, and that is ITR plus 2. So, that is the value of C we are getting. So, now this is the value we are getting. So, A and B, and then again the C value will come, and then I will write the value of here control V. So, f print f. So, this is the iteration initial A. So, this is not the value of these iterations A and B I am getting, and then I will put the end of this over. So, from here I will get my root, that is equal to C, and the number of iterations, so that is equal to ITR. So, that is the value we are going to get, and I will save this function as regular. Now, I will go to the main program. So, this is the program we are going to get. So, in this case also we have to this one I just make the comment, and all other I will so in the bisection method I know that 2 initial approximation are needed. So, I will use this one. So, I will take my f here and then my a and b is -1, then is equal to tolerance I am taking 0.5, and then from here I am calling this regular falsy method, and the regular falsy I am, so that is the 3 conditions are there. So, you just copy and here you can write, so that you should be able to know that how many number of input I have to pass. So, I am putting AF, AB tolerance, so that is okay. So, I have to just write here regular, and then from here I am getting my root, and this is the number of iterations ITR, and then I am getting my X list. So, in that case if you remember the initial solution, the exact solution was coming, I think, so in this I have to write my X exact. So, that is, suppose I am taking 0.5771. So, that was the approximate root we were getting in the case of bisection method. So, let us check that whether we are able to get this result or not. So, I will run this one and let us see. So, that is the we are getting. So, I started with -2 and -1, and after that, okay. So, in this case I am getting this root -1.86, okay. So, it means I am doing let us see here 1, 2. Let us see what is my f. So, I just put the value of f 0, it is coming 1, f 1, f 2, okay. So, I have to choose 0 and 1, right. So, let us choose 0 and 1. So, let us choose this one. So, now you can see that what are the results. So, let us see. Yeah. So, from here you can see that I am getting my initial approximation 0 and 1, and with the time as the iteration passes I am getting my solution 0.517756. So, that is the approximated solution I am getting, and the rate of convergence started with 1.53 and then it is reduced to 0.333. So, in this case for these initial conditions I am getting the rate of convergence is 0.33, because this is a regular falsy method, and we know that in the regular falsy method the rate of convergence is 1.61 or 1.62. So, but that is the maximum rate of convergence we can have, but in this case based on my initial condition, and I am finding for this rate of convergence 0.33 for this case, but it is it will be definitely less than 1.62. So, that is the rate of convergence we are getting for the regular falsy method, and in this case I am already told you that for this type of equation we do not know what is the value of x exact. So, here also I am choosing my approximate value of this one. So, if I choose the approximate value of the solution, then also it may happen that the rate of convergence will become lesser than the whatever expected. So, that is the case here we are getting. Okay. So, this is the way we have found the regular falsy method, and then based on the regular falsy method and the Newton method we have shown that how the rate of convergence can be applied or can be approximated within the same program, whatever the program we are writing for the regular falsy and the Newton-Raphson method. So, in the maybe in the next lecture we will continue for this one. So, thanks for viewing this one. Thanks very much.